We ended up using our calculator to evaluate derivatives at a given point. We talked about the button presses for that on 83s and 84s. We did an example together. So then we ended up at example 7. It says, use your calculator to find the derivative of the 3 examples at the beginning. What problems do you find and why? Again, this is referring back to those 3 problems we did at the beginning of our notes where we graphed them. We saw that at a corner, at a cusp, and when we have something like a cube root function that has a vertical tangent line, then even at points that are continuous, we can still have places that are not differentiable, okay, that our calculator can't always see. So let's look at those same 3 functions in our calculator. All right, for the first one, again, button presses. In these examples, I've taken the time to put each function into y1, y2, and y3 just to make it go a little quicker. All right, so that we can just call on those functions. So again, we can press math 8 to get to n derive. And we want to take the derivative with respect to x. And I put that function into y1. So I'm going to press alpha trace, call on y1, and our x value is at 3. All right, and we evaluate, and it says at 0, but we know that our function is not differentiable at x equals 3. We saw that in our first example. All right, that's a corner. Okay, but our calculator doesn't tell us that. So what I want you to learn from these 3 examples is to not rely on your calculator all the time, and to actively seek out these pointy places and vertical tangent lines before you start to use your calculator. Okay, or even if you just look at the graph, that would be helpful as well. All right, so for the second one, we can also do alpha window, and n derive is option 3. Doesn't matter, it does the same thing either place you go. We're still deriving with respect to x. This time I want y2, so I'm going to call on y2, and we want it when x equals 0. Again, this was that cusp, the winged function, and again it tells us when x equals 0, our derivative is 0, but we know that's not the case. It's not differentiable at a cusp. We saw that already. Okay, so again, be careful. And then lastly, for the cube root function, if we derive with respect to x of y3 when x equals 0, now it tells us 100, and again, that's because that vertical tangent line, and we talked about how the slope as it approaches from both sides is approaching infinity, and that our calculator uses this symmetric definition of derivative, and again doesn't always get it right at these special places. So keep your eyes out for that. All right, example 8 says determine if f of x is differentiable at x equals 1, and they give us a piecewise function. So the 2 things we need to check for differentiability, going back to our definition in our notes. Okay, so we said from our definition that we had in a box that we highlighted, we said the limit as x approaches from the left and the right at our point of interest, the slopes have to be the same, right? The slopes have to be approaching the same value on either side, and that slope has to be a finite value L. Right? And then we said that if a point is differentiable on a function, then the function must be continuous at that point. Okay, so those are the 2 characteristics of differentiability at a given point in a function. So those are the 2 things we want to look for when we're asked, as we are in example 8, to determine if a function is differentiable at a point. especially in a piecewise like this, we got to check those two things. All right. So number one, the slopes. So if we find the derivative of each piece, okay. So for x squared, for time's sake, I've taken liberty to find that derivative, which is 2x for any given x value. And the second piece is linear. And so we just take the slope from in front of the x. That's going to be 2 for any x value. All right, so coming from the left, we're approaching 1. We plug in 1. 2 times 1 gives us 2. Coming from the right, it's going to be 2 regardless of what our x value is. So slopes are the same. Check. Second part is continuity. So since we're approaching x equals 1, this is where our piecewise is split. So we got to make sure that we're getting the same y value at either end, and there's not a gap or a jump discontinuity. All right, so x squared, our first piece, has to equal 2x plus 1 at that point where our piece is split. In this case, x equals 1. Okay, or honestly, just whatever our point of interest is. All right, which for these kind of problems is typically going to be where our piece is split, but make sure you check on that. Set them equal to each other, substitute in that 1 for x, and in this case, we've got one side with a height of 1, one side with a height of 3, so they don't link up. Right, those train cars don't hitch up. So because it's not continuous at that point, it can't be differentiable. All right, so for a problem like this, you want to show each of these two main pieces, and then you want to explain yes or no and why. All right, example 9, similar problem. We're still going at x equals 1. The only thing that changed was in the second piece, we've got 2x minus 1 instead of 2x plus 1. All right, but let's take the same thing. So let's start with slope. All right, the slopes for each one is actually going to be the same. All right, so slope of x squared for any point is 2x. For 2x minus 1, slope is 2 for any point. So they're going to line up to be 2. Good to go right there. All right, for continuity, same thing. Let's set each piece equal to each other. Let's let x equal 1. In this case, we're going to find they do line up. Okay, so that 2x minus 1 shifted down to essentially from the 2x plus 1, so that they both have a y value of 1. They link up, so it is continuous. So then it's continuous and the slopes line up on either side, so then we can conclude that f of x is differentiable at x equals 1. All right, so that's the last of our notes for this unit. One other thing I wanted to bring attention to is on the week 5 plan page in Canvas. Scrolling down underneath the plan, underneath most stuff, under the extra resources, there's a couple of really good resources that I meant to draw out today in class and didn't. This first one, this great GeoGebra visual tracing sketch, is really great for understanding the graph of a derivative as it compares to the original function. So I encourage you to kind of play around with this one and the next one that I'm going to show you. You can change the function to whatever you want it to be up in the top. All right, if you've never used GeoGebra, it's real similar to Desmos. And you can kind of play around with these buttons and check the function and whatnot. The other one is similar, the one underneath it, another great GeoGebra illustration, but it draws out, it makes another cool connection to the those actual y values of the derivative when you use this slider here. I'll let you guys explore that one, but same thing, you can kind of put in whatever function you want to see the shape of what the derivative creates. All right, it's going to be really important to make those connections to the graphs of the derivative. And then if you want more practice with kind of like what we did in that Desmos card sort of matching a graph of a function to its derivative, then there's some, it's kind of like endless practice. You just keep excuse me, they give you 4 functions and 4 possible derivatives, and you line them up and see which ones go to which. And you can say evaluate, boom, you got 10 out of 10. You can say load new, and it gives you 4 new ones. All right, and it's just good practice. It'll give you instant feedback. Yep. All right, so a couple of good resources. If you want more instruction, again, the Khan Academy resources, they've got good practice, they've got good video instruction, and make sure that you try the problems on this review sheet and come with questions on Thursday. See you then.